Hi everyone. So the next topic is design of distillation column. At the end of this class, you should be able to explain why the ratio of vapor and liquid velocities in a column is important, and also for you to familiarize with the basic methods of the calculation for column diameter and height based on the flow rates of vapor and liquid in the column. So when you design a distillation column, your goal is to first, of course, to maximize the separation um, to obtain the product purity at the desired specification. But at the same time, you want to, of course, minimize all the costs associated with designing the column, i.e. the manufacturing and installation cost, the energy operating cost, the maintenance cost, and also other than the cost and to achieve the desired product specification, you also would like to design your column such that it will provide some operating flexibility. Let's say if you have different feed flow rate with varying composition from time to time within 10%, for example, or at different times maybe you want the product purity to be higher or lower than the design uh, the original design, so you want to provide some flexibility in that. So some basic terminology for the internals of a stage column. So when you have a column, the column have trays. So all this while you have been calculating the number of trays, but how exactly does it look like? So when you look at the internal of the column, this is the tray. Okay, this is the tray. This is the tray where it provides the vapor liquid mixture, and it serves as an equilibrium stage. And also, so the vapor rises at the holes of the trays, and then the vapor will mix with the liquid in the tray, and the liquid will flow down the tray through the downcomer. So this is the downcomer. So it is an opening in the tray which allows the liquid to flow down to in the column to the next stage. Okay, so this is the downcomer. And then there's a weir. So this is the weir. Weir is just a dam to hold the liquid mixture to provide depth uh, so that the liquid and vapor can mix and reach equilibrium. So these are some basic terminology in the column concerning the trays. Okay, so there are various types of trays based on the geometry, how the vapor and liquid flows through the tray specification. So one of the tray types is sieve or perforated. If you were in UM, I would have advised you to take a look at different types of trays in a distillation column at the staircase near the pilot lab, but you can do that whenever time permits later. So this is an example here for a sieve or perforated tray, simply a tray with vapor holes. So the vapor will go through these holes and mix with the liquid on the tray. Okay, so the arrangement, number and size of the holes are the design parameters. You may have different hole diameter and different spacing between one hole to another. That is something that you can consider in the design of the trays. The type of tray is the bubble cap. So if you have a look at this tray, so these are the bubble cap. A cap is placed over the tray's vapor hole. So in this bubble cap tray, the flow arrangement of vapor goes through up here, and then it mixes with the liquid, and then the liquid will go through the downpipe. The downpipe here is like the downcomer. Okay, you use a valve type of tray. So in the valve trays, the perforation, the holes in the trays are covered by liftable caps. So these caps will be lifted when vapor flows through the caps, so creating a flow area for the passage of the vapor. The lifting of the cap directs the vapors to flow horizontally through the liquid. So this provides some sort of better mixing than is possible in a sieve type of tray. In this slide, you can compare the different flow paths of vapor and liquid in different types of trays. So in part A, is the perforation or sieve type of tray. So simply the vapor flow upwards and mix with the liquid. Whereas for part B is the valve cap type of tray, and for part C is the bubble cap type of tray. Then part D is the trays with valve cap. This is actually part D. Okay, this is how it looks like for the trays with valve cap. So when you design your trays, your goal is to first maximize the column efficiency. So what factors affect the efficiency is the mixing between the vapor and liquid phases. You want to enhance the vapor and liquid mixing, maintain optimum vapor flow and also the liquid depth to make sure that the vapor and liquid have enough residence time for mixing and reach equilibrium. At the same time, you want to minimize pressure drop and also to prevent fouling. But this one, fouling is a lot more related to the chemical properties of the fluids. So when we design a column, there are three things that we want to avoid, which are the flooding, weeping, and foaming. So what are these three things? So let's say you have a column, okay? So you know your column have some trays, and then you know that in the column, the vapor flows upward. These are the red ones are vapor flows, and the liquid flows downwards. Okay, so when the vapor flow rate is very high, the liquid cannot come down. So this will cause flooding. Okay, or otherwise, larger liquid flow rate also can cause flooding because then it's not balanced between the vapor flow rate and liquid flow rate. And whereas weeping, so for weeping, it occurs at low vapor flow rate. So when the vapor flow rate is very low, it cannot entrain the liquid in each tray. So when the vapor flow rate is very low, the liquid keeps coming down. It weeps down the column. Whereas for foaming, foaming occurs when the components form a stable foam. When there is foaming, the efficiency of the column is compromised and the column may also flood. So here, what you want to know is that you need to have a reasonable ratio between the liquid flow rate and the vapor flow rate. So now that you know why the liquid and vapor flow rate in the column is important, it's important such that you can find the area of stable operation in the tower. So when you know a liquid flow rate, let's say liquid flow rate is here, some numbers, and molar vapor flow rate is here. So you want the vapor and liquid flow rate to be within this area of satisfactory operation. You don't want it to be in the weeping area, or you don't want it to near the weeping point or the dump point, and you don't want also for the liquid flow rate and vapor flow rate to be outside this envelope. Okay, you don't want it to be excessive entrainment, flooding, and so on. You want it to be in this area of satisfactory operation. So that's why you need to know to adjust the vapor and liquid flow rates. Okay, so what are the steps that we do when we want to design a column? So first of all, we need to calculate the flow rates. So you know that when you have a column, given the feed flow rates, and then you calculate what is the flow rate of the top and bottom products. So this one will be done using a mass balance. So it's either mass flow rate or molar flow rates. And also you have to keep in mind that you have the different flow rates in the stripping section and in the rectification section. Next, you can determine the column height. So you need to determine the number of equilibrium stages to know the column heights. So from the number of equilibrium stages, you can determine the column height by specifying the plate spacing and the depth. Okay, but that is if you are doing the plate column. Sometimes for the next chapter, we will be talking about pack column for absorption and also can be used for distillation. So in that case, you need to know the total height of packing. And then next is to determine the column diameter. So for the column diameter, this is where you need to know the vapor velocity, and then if you know the volumetric flow rate of the vapor and liquid flow rates in the column, you given the vapor velocity, you divide the vapor velocity with the vapor flow rate to give the area. So when you got the area, you can get the diameter. So now you have the height of the column and the diameter. So you have a rough idea on how your column is sized. Okay, so it is important for us to determine the correct vapor velocity for our column, and these velocities may be different depending on the section in the column, either rectifying or the stripping sections in the column. So they may be different. So as mentioned previously, if the vapor velocity is too low, then weeping may occur. If it's too high, then flooding may occur. So liquid will backflow to the next plate or to the previous plate. So what you want to do is to find the correct velocity somewhere in between to avoid weeping and to avoid flooding. This also depends on the tray type, because the tray type will determine the vapor flow, the way how the vapor and liquid flow in the plate. Then you need to also calculate the upper limit for velocity of the vapor at the point at which flooding occurs. So normally you want to find out what would be the flooding velocity, i.e. what would be the velocity of the vapor such that flooding will occur, and we will normally use a design velocity of 80 to 85% of the flooding velocity. So the keyword here is to find out what is the flooding velocity. Then we use the vapor velocity of 0.8 to 0.85 times the flooding velocity. Flooding. Okay, and this one, if you want to refer more, you can refer to this book, Coulson and Richardson, Volume 6, Chapter 11.13. Way to determine the suitable vapor velocity, all of these, bear in mind, are the empirical correlation. Okay, so empirical correlation meaning it's what have been practiced. There's no really a scientific explanation as to why this formula is used, but rather it's based on experience. So one way is to use this equation. The UV here is the maximum allowable vapor velocity based on the gross or total column cross-sectional area. So LT here meaning the plate spacing. So in your column, what is the space between one plate to another? That is your plate spacing. And then rho L is the liquid density, rho V is the vapor density. So this is one way to determine the vapor flow rate, the maximum allowable vapor flow rate. Okay, so how do we determine the flooding velocity? So for either section, i.e. for the stripping and rectifying section, so you need to determine what would be the flooding velocity for the different sections in your column. So UF, i.e. the flooding velocity, can be calculated when you know the liquid density, vapor density, and you need to find out the K1. K1 is a coefficient which you can obtain from a chart, which will be shown in the next slide. So in the previous slide, you know that you need to find out what is K1, the coefficient, and then to get K1, you need to calculate FLV. So this the chart of K1 versus FLV is available in most books on distillation. For example, the McCabe-Smith book, Coulson Richardson book, etc. And this chart is specific to the type of tray, e.g. sieve tray, valve tray, bubble cap tray. So you need to decide what kind of tray you want to use, and then use that chart to find out what is the value of K1. So you need to find out what is FLV. So the formula is given here. FLV equals to LW. So LW is the liquid mass flow rate in kilogram per second. VW is the vapor mass flow rate in kilogram per second. And then the rho V and rho L are the density of vapor and liquid respectively. So you need to know the flow rate, mass flow rate, and the density. You can calculate the FLV. Yeah, there are some restrictions applying to this chart, such as the minimum hole diameter, wheel height, etc. But let's stick to the basics of the process of designing the column, okay? So now we want to find K1, so you need to calculate FLV. So this is an example of the chart of K1 versus FLV from the book of Curtin and Richardson, volume 6, 3rd edition, page 567. So in this specific edition, if you have a latest edition, then the page numbers and everything may be different. So when you have calculated the value of FLV, then let's say you decide what is the plate spacing. This plate spacing also depend on the tray type. Okay, normally, okay, let's say you use plate spacing 0.6, then you need to refer to this curve. So when you calculated the value of FLV, let's say you get some value, and then you know this is your plate spacing, then you read what is the K1 value from this chart. So once you got this K1 value, you can calculate the flooding velocity from the formula given in the previous two charts. Okay, as mentioned, the column diameter depends a lot on the vapor flow rate. But the vapor flow rate in the sections may be different. In the rectification section may be different from the vapor flow rate in the stripping section. The flow rate from these sections, from either sections, can be converted from kilomole per hour into meter cube per second. So you should know by now how to convert vapor flow rate from kilomole per hour to meter cube per second. Well, for starters, you may assume ideal gas, CPV, and RT. Then you can get the the flow rate V in terms of meter cube per second. Okay, so let's say you have this flow rate. So to familiarize with your fluid mechanics lesson, Q. So the unit of Q is the same with the unit of V, is the same with meter cube per second. So using the continuity equation, Q or Q, capital Q or small q doesn't matter, equals to VA. So the V here is the superficial velocity. If you decide on the velocity in meter cube per second, the unit is meter cube per second, then you can find A, the area. So area is, the unit is meter squared, then you can find out what would be the diameter of the column. So if you have a column with two sections, rectification section and the stripping section, you have different diameters. So let's say this one will give you D1 and this one will give you D2. So you have two different diameters. Normally we would just design the column using the one diameter, because you can't be designing a column with different diameter. Maybe it's possible, but it's just too much hassle and maybe it doesn't look that nice. So we would normally use the larger diameter to design the entire column to simplify the construction. And if we decide this, then the plates in the lower velocity section will have less perforation. Okay, it will have less number of perforation, less number of holes in the plate to compensate with the larger diameter used for that section. Alright, another good practice is to always check whether weeping will occur or not in your column. So in order to avoid weeping, you have to decide on the minimum velocity to be greater than this value. So what you do is you calculate what is the minimum vapor flow rate that can be used for this, not, meaning, sorry, vapor flow velocity. So you need to find out what is the minimum velocity at minimum flow rate, then decide that the velocity and the flow rate must be greater than minimum to avoid looping. So to get this value, you can use this formula. Again, this formula is empirical. This is not the definite formula that you should use, but rather as a starting point, you can try to use this. So K2 here is the constant, and you need to read from the chart. Depends on the plate. And then DH here is the hole diameter. So depending on the plate, if it's a sieve, And then the hole in the sieve, we need to know what is the diameter of the hole. And then rho V is the vapor density. So yeah, knowing all this value, read the K2 value from the chart, then you calculate the U min and make sure your velocity and flow rate is above the minimum to avoid leaping. Okay, so when you calculate the column diameter, the minimum column diameter for trade column normally is typically is 0.75 meters. If it is smaller than 0.75 meters, normally packed column will be used instead of a trade column. So this if this is the minimum diameter, what would be the maximum diameter of the column? It can be quite large, up to 5 meters. But sometimes if the column diameter is too large, you may want to decide to operate with two or more separate columns in series or in parallel to replace the large diameter of a single column. So what would happen as the column diameter decrease? When the column diameter decrease, the vapor velocity increase for a given vapor flow rate. Well, you can read the rest of the slide here. So at the end of the day, when you calculate the column diameter, you need to have a look at these numbers. Okay, these are rule of thumb. It's not right or wrong. There's no right or wrong design when you design a distillation column. You just need a design of a column that is functional, that is logical, that you can construct, that you can transport from the fabrication site to your operation site, and also most of all, uh, you have to make sure it's functioning. So you want to avoid flooding, entrainment, and leaking. So these are the things that you need to consider when you calculate the column diameter. At the end of the day, the final consideration is the column cost. If you have a large diameter column, it's more expensive than smaller diameter column. However, you need to take into account the economies of scale. Okay, moving on to the other factors when you design. So you need to also take into account the total area of the tray hole openings, and then this is based on the vapor flow per tray to prevent weeping, minimize pressure drop, reduce entrainment at a given vapor velocity. The layout of the tray holes, and then the liquid depth of the trays, hence the weir height to ensure mixing and to reach equilibrium as far as possible, increase liquid and vapor contact time, and also to prevent a spray regime that reduces the efficiency. So after you have calculated the column diameter, next is you need to determine the column height. So if you have the certain diameter, then to determine the height, of course the height will correlate with the tray, number of tray, and then hence the tray spacing needs to be taken into account. So what would you decide for the tray spacing, or the space between one tray to another? So the factors that you need to take into account is the maintenance access. Okay, so these are all rule of thumb. Typically, you would allow 0.15 to 1 meter of spacing in columns with less than 6 meters of diameter. But if you have a larger column, then you need to have larger spacing to allow for maintenance access. Yeah, how do you maintain the column? So would there be a person needing to come inside the column and clean the trays? You need to take into account those factors, because if anything happens, let's say fouling, or let's say if some of the plates got rusted and disengaged from the column, so what are you going to do? So you cannot just calculate the number of stages and calculate the diameter and the height and that's it. No, you have to think about everything, because well, that's the job of the engineer. Okay, there's a lot of factors that you need to take into account or you need to consider when designing a column. Another factor is the type of tray. So you know that as a basic knowledge is you have sieve trays, valve trays, and bubble cap trays. So what kind of trays are you going to choose for your column. So you need to take into account these factors: the cost, the pressure drop, efficiency of the column, the vapor capacity, and the turn down ratio. Okay, so you don't just choose sieve trays because it's the cheapest, and or you don't just choose bubble cap trays because it's the highest efficiency and you can cope with the cost because it's just capital cost. No, you need to take into account the flow of vapor and whether the fluid materials are suitable for that trays or not. So that's why in designing a column, there's no right or wrong answer, and there's no one specific recipe that will work if you want to come up with a column. But most basic is diameter and height in this course. Just some final notes on the design of a column, especially the diameter. Well, previously we assumed that CMO, constant molar overflow, applies, but actually sometimes in a lot of cases the CMO is not really applicable. It's just a mere sufficient approximation. So what you want to do is to calculate the column diameter at each stage, because each stage may have different flow rates, different vapor and liquid flow rates, thus need different diameters. And if you calculate the diameter for each column, and you will have to decide to use the largest diameter for the design, and to compensate for the other stages with smaller diameter, you design the other stages with less number of holes or more widely spread holes in the trays. But you can also design a column that has different diameters at different section of the column if it is cost effective to do so. Or if it's too large for the column diameter, then it will lead to excessive whipping in a given section of a column. So, you have to do a trial and error and see if your design works and see if you can get the desired purity of the product at the top and the bottom of the column. So let's say finally you manage to obtain the column diameter at the end of the day. You will have to usually round it up to the next 0.5 feet or the next 0.1 meter increment, because, well, they don't design custom-made column trays, but rather you have to take the trays and shelves from the shelf of the manufacturer of the shelf. So you need to find the one that is uh, the closest dimension to your column. Just like when you study fluid mechanics previously, when you decide on the pipe sizing, you need to find out the nominal bore that is standard, not just simply ask the manufacturer to do a custom made pipe size for you for your system. Okay, so now that you know how to calculate the diameter and the height of the column, this is not the end of the design. There are a lot of other things that you need to consider into your design. What will be the column and tray materials? These are technical design, technical consideration. So you have to take into account the material to be suitable for your fluid. If it is corrosive, then you can use something that will corrode in time. So you have to build your column to last for at least 10 to 20 years. You don't want to build your column and then decide that, oh, it's not going to work in just 1 or 2 years or even less than that. So you need to take into account a lot of things when you design. And then another one is to think to consider the column insulation to prevent heat loss, and also the transport properties of the fluid, the viscosity, the density, the surface tension to ensure sufficient mass transfer. Yeah, that mass transfer. So, and then you need to think of the cases of non-ideality. What if there's a change in your operating condition? What if your feed temperature changes? What if you need to supply the distillate at a lower or higher temperature? And then changes in the feed or product specification, purity, and stuff. Safety, yeah, this one is very important. Safety of the operation. This safety relates with the process control, which you will learn in your third year. So you need to take into account the flow control, temperature control, the pressure control, composition control. Um, yeah, think about all those, and piping and instrumentation. Um, also relates to the instrumentation relates to process control, the piping for the mass transfer and transport properties, energy requirement. Yeah, this is also an important part. Design of reboiler and condenser, flow rates of the heating and cooling media, and a lot of other things. This is not an exhaustive list. You can think of many possibility, like what would happen if there is a natural disaster, if there's a pandemic, for example, things that you don't think it would happen in your lifetime, but then somehow it happened. Maybe it's not really related to the distillation column, but the point is, other than technical consideration, you need to also take into account things that you cannot control, but what are you going to do if it happens? So that's all for the design of distillation column topic. So additional references, if you'd like to read more, you can refer to these books. I'm sure these books are very, it's going to be useful for you in the IDP and also for the design project in your final year. And yeah, that's all for now. So at the end of the day, you need to calculate the diameter, the height, and at least the condenser and reboiler duties. For this chapter, for this course, it's enough for now. Okay, thank you very much.